Hey folks, we left off talking about limits, and now we're talking about continuity. Continuity at a point. This is a hugely important topic. This is something we talk about over and over and over and over again in this course. So what is the requirement if I want to get across the chasm smoothly, as he says, safely and smoothly? I need all three of the things to be at the same height. So I need the road coming in, the road coming out. I could think about this as coming in from both sides, but road coming in, road coming out, they need to be at the same height. And then the bridge itself needs to be at that height, right? So if this was way up here at like 30 feet higher, I would not have this sort of smooth transition. It would be, woo, we'd have to rush down. So the idea that you want to think about is continuity. You need all three things to be at the same height. You need the point, and the two bridges, the function values coming in from either side, they all need to be at the same height. So our theorem says a function is continuous at a point if, remember what this little limit with the minus sign means, from the left. Remember what this limit with the little plus means, from the right. So that's saying that the limit from the left and the limit from the right equal the actual function value. So let's write that again in a little note. Let's write it limit from the left. Notice that doesn't say going left, it says from the left. This is the limit from the right. And then this is the actual point. So, using our definition of continuity, determine whether the graph of blah, blah, blah is continuous at the following point. So x equals 2, x equals 0, and x equals negative 10. So what I'd like to do first is I'd like to organize, what does it mean? What is this definition of continuity? What are the things that I have to show? What are the things that I have to prove? Number one, I have to prove the function value is defined. So I have to prove that there's a point. I can't have the smooth transition across the chasm if there's no bridge. So I need the point. Number two, I need to prove the limit exists. I need to prove that the two roads coming in are going to be at the same height. And the way we prove that is prove that the limit exists. This is talking about the one-sided limits are equal. I guess I could go back up here. Prove the function value is defined. Does f of c exist? Question mark. And c is just some random thing, some random value, wherever we're trying to figure out. Like c would be 2, c would be 0, c would be negative 10. So I need to prove that the function value is defined. I need to prove that there's a point. I need to prove that the limit exists, which means I need to show that the one-sided limits are the same number. And then I need to show that the one-sided limits are the same as the point. So that's part 3. Prove the limit equals the function value. Now, this is something that you could memorize. That is possible. But I'd rather have you just understand and think about what do I have to do to show that a function is continuous. For me to prove that a function is continuous, I have to have the bridges. So I need the limits to come. The limit represents the roads coming in, and I need to have the bridge, and I need them all to be at the same height. So let's practice one together. So let's start off by trying to prove that the function value is defined. What that means is I need to plug in 2 in for x and see what I get. So number 1, h of 2, h of 2 equals, let's see, 2 cubed is 8, minus 4 times 2 is 8. Oh, that's scaring me already. Put a 2 in the bottom, that's 4, that's 16. Minus 20. 8 minus 8 is 0. 4, 16, 20. 20 minus 20 is 0. What does this mean? I know already. My graph has a hole. And if my graph has a hole at 2, can our function be continuous? There's no bridge. So could you get across the chasm? No. So we would say something like this. H is not continuous at x equals 2 because h of 2 is not defined. And our proof is that work up above. That work that we showed right there, that's the work. That's all you got to do to show your work. All right, let's try this again at x equals 0. So number 1, let's see if the function is defined at 0. So h of 0 equals, so that'd be 0 cubed, which is 0, minus 4 times 0. Uh-oh, my math voice is starting to set an alarm. Then I would have 0 plus 0, subtract 20. Oh, 0 minus 0 is 0. 0 plus 0 minus 20 is negative 20. What's 0 divided by negative 20? 0. So we do have a point. H of 0 is 0. Now, it's not a point that we love, but it is. You can have the point 0, 0. So we're in good shape here. Let's try the next thing. Now we've got, so we know we have a bridge. We know that the actual point is alive. Let's see if the limits meet at that bridge. So what's the limit of h of x as x approaches 0 from the left? So again, what I would do to figure this out is I would plug 0 into this equation. And when I plug 0 into this equation, I get 0. The limit of h of x as x approaches 0 from the right, from the other side. So I put 0 into my equation again. This is called direct substitution. And we get 0 again. These two things together, these mean that the overall limit as x approaches 0 equals 0 because they both approach the same place. What do you think? All right, so we've shown that we have a point. We've shown that the limit exists. The last thing we have to show is that the limit and the function value are the same things. So we would say h is continuous at x equals 0 because h of 0 equals 0, which equals the limit of h of x as x approaches 0. This equals 0. This equals 0, so they must equal each other. Or another way you could write this if you wanted to, you could also write this like this. H is continuous at x equals 0 because the limit of h of x as x approaches 0 from the left equals h of 0, which equals the limit of h of x as x approaches 0 from the right. So you can write it up this way too if you want to write it with the one-sided limits, just like he wrote it here, just how Corpy wrote it right there. What I chose to do was I chose to show that the overall limit existed, and then I showed that the limit and the point are at the same height. Let's try it again for x equals negative 10. Number one, I need to figure out if h of negative 10 exists. Hey boy. So negative 10 cubed would be negative 1,000. Negative 10 times negative 4 is positive 40. Over negative 10 squared is 100. Minus negative 10 times 8 is negative 80. Minus 20, which turns out to be, I don't want to even mess around with what that is, because I noticed on the bottom, 100 minus 80 is 20. 20 minus 20 is 0, which means, what do we have here? At negative 10, what do we have here? Come on, you got to get to the spot where you start to memorize these. So I've got a 0 on the bottom and not a 0 at the top. That's the worst thing that can happen in all of mathematics, which means it's going to create the worst thing that can happen in all of graphing, which is a VA. So let's write this up. Is h of negative 10 defined? It is not. So the function value does not exist. The game is over. So we would say h is not continuous at x equals negative 10 because h of negative 10 equals DNE. We could write it up like that. We don't have to always say undefined. I think it's probably more proper to say that it's undefined, but it doesn't have to be. So, all right, so we have this removable point discontinuity. What do we call that? We call this a hole. A removable point discontinuity is a fancy way of calling something a hole. So we have, let's talk about removable real quick. A removable discontinuity and a non-removable discontinuity. A removable discontinuity is something easy to fix. So if you have a graph with a hole in it, how many points would you have to fix, quote unquote, to fill that hole? One. You just have to figure out what's going on at that one spot. We have a non-removable discontinuity would be something like a vertical asymptote. So let's just write it down. So removable would be something like this. That's easy for me to fix. I would just figure out what height that is. I would take whatever the x value is and I'd plug in a point there. I could even, if I had a point, we call this a holy jump. I call this a holy jump. Sorry, nobody else does except me. I could take this and I could just push it into that spot and all of a sudden we don't have a hole anymore. So these are removable. These are easy to fix. Non-removable would be things like this. And I think I'm going to review this with you later, but let's see. That's called a jump. I would have to move infinitely many points. I'd have to grab all these points and slide them down, which would take a lot of work. We couldn't remove that easily. Sticking with that same sort of logic, if I had an asymptote, for me to get these two parts of the graph to touch each other, to be continuous, I would have to move infinitely many of these points down here and infinitely many of these points up here and squeeze them together. So that's what we would call non-removable discontinuity. But we're talking about a removable discontinuity. In this case, this is the hole is what we're referring to here. So, wouldn't you know if you have a removable discontinuity or a hole? If your limit exists, but when you get to the point, either the point is undefined or the point is not the same as the limit. So you know you have a limit, but either there is no point there, that was this scenario where I covered up, there is no point there, or when you get there, the point is not the same as whatever height your limit is. So we would call this a hole. Let me grab a different color that would show up. I shouldn't have used blue. If f of c is undefined, this is a hole. If f of c does not equal L, this is a holy jump. And I'll talk more about what a holy jump is. I'm sure somebody will ask a question. Now, it looks like Corpy only... Hold on a sec. Okay, where were we here? Okay, so yeah, we've got this thing called a hole. That occurs if you have a limit, but the point is not at the limit. Sorry, the point doesn't exist, or the point and the limit are at different heights. This is a removable discontinuity called a hole. And the hole is at the height of the x value here. Okay, look at all these x approaches c. And at the height of the limit is where the hole is, which is different than where the actual point might be, could be at a different value. I'll show you some examples when I'm talking about of that. Okay, so we know the function value and the limit exist. The limit value exist independently of each other. So again, what that's saying is the point, the actual value versus the intended intended value are independent. So where the graph intends to go and where it actually goes are two different things, okay? But the one-sided limits may also exist independent of each other. So that's that situation I was talking about. Remember, the one-sided limits are the bridge? That's this scenario, and I'm going to give you an example of what I'm talking about here. But that's where one side of the bridge is going up to 100 feet above the ground, and the other side of the bridge is going 100 feet below the chasm. They're not going to meet up very well, or at least the bridge in between is going to be a mess. So let's take a look. So we got a piecewise function. A couple things to keep in track. We kind of look at this, kind of think about things, all right? This is a parabola for all the x's that are smaller than 2, less than 2. This is a linear function for all the x's that are greater than 2. So when we do a piecewise function, we talked about this in pre-calc, I'm going to evaluate this at x equals 2. Right away, something weird should be jumping out to you, because this is the function if you're less than 2. This is the equation if you're greater than 2. So what happens when you are 2? There is no point. So f of negative 2 is undefined. If I was trying to figure out continuity, I could already say that this is not going to be a continuous function at x equals 2. Now, what's the limit of the function as x approaches 2 from the left? Now, this gets kind of interesting. The limit of my function as x approaches 2 from the left is equal to, so which one of these equations is the equation that you would look at if you're coming towards 2 from the left side? So these are all the x's that are smaller than 2, that are less than 2. So if I'm approaching 2, I'm using this as my equation. So I would plug in 2 into this part. That would be 2 squared, and 2 squared equals 4. So the limit from the left is 4. Now let's figure out the limit from the right. So what's my limit? What's my function doing as x approaches 2 from the right side? So I go back up here. All of these are x's that are greater than 2. So if I'm coming to 2 from the right side, maybe it's better with a little drawing. If I'm approaching 2 from the right, I'm coming from numbers that are greater than 2. If I'm approaching 2 from the left, I'm coming from numbers that are less than 2. X approaches 2 from the left. These are all x's that are less than 2. X approaches 2 from the right. These are all x's that are greater than 2. Does that make sense how I'm looking at this over here? I'm trying to decide which one comes in from which side of 2. So as I approach 2 from the right, I'm going to use this as my equation. So that would be 2 times 2 minus 1. I can direct substitute. 2 times 2 is 4. Take away 1 is 3. All right, we've got a problem here. So what's the overall limit? Remember, the overall limit is what's happening to the one-sided limits at the same time. So one of my roads is going to 4, my other road is only going to 3. This graph does not meet up. So we would say that the limit, the overall limit, the limit of f of x as x approaches 2 equals d and e. It does not exist. I wish I wouldn't have boxed it all in. I wish I would have just boxed in d and e because that's what I did up here, but oh well. Okay, so what's the continuity? We've got a big problem here. We've got a lot of reasons why f. Actually, you try to do this. Excuse me. You try to do this. What's the continuity of f at x equals 2? Pause. All right, let's see. F is not continuous at x equals 2 because, and then you could go 2 ways. I'm going to write up, actually, you could go 3 different ways. There's lots of reasons. Because f of 2 is undefined. So we don't have a point. We could also say, or we could say the limit of f of x as x approaches 2 from the left does not equal the limit of f of x as x approaches 2 from the right. There's another thing that we could say. So the one-sided limits aren't equal. Or we could say that the function value f of 2 does not equal the overall limit as x approaches 2. Any one of those would be fine. We call this a jump. This is a jump where the 2 branches head to a different height. This is a jump discontinuity. Continuity. I always have a hard time spelling that word. A jump discontinuity. So coming down here, let's kind of formalize this. This is what we call a non-removable jump discontinuity. So just to review quickly, non-removable means that you'd have to move more than just 1 point to fix it. I couldn't just take this 1 point and put it up here because then these other points would all be too low. I'd have to move infinitely many points to get those 2 sides to touch. Here's an example of a bridge. One side of the bridge is too high for the other side of the bridge. Now you could build a connection, but it wouldn't be a nice smooth transition from one side to the other. We know we have a jump discontinuity is if the limit from the left is some number, L1, and the limit from the right is some number, L2, and L1 does not equal L2. So they are not at the same height. We would say then that F has a non-removable jump discontinuity at that C value. So we've talked about a hole discontinuity, which is a removable discontinuity. We've talked about a jump discontinuity. And now we're going to start to talk about some other types of discontinuities. Well, let's just do, yeah, we'll get into those in a minute. Oops. So, use the definition of continuity at a point, discuss the continuity of the following functions. So let's start off by kind of just looking at the functions themselves. What kind of function, what group of functions does x plus 2 x squared over 2 and 2 belong to? These are all things called polynomials. A polynomial function is a function that is like, I call it normal. There's nothing weird going on. There's no square roots. There's no absolute values. There's no x's on the bottom. There's no fractional exponents or negative exponents. It's just like a bunch of normal equations, like what you would think of when you think of an equation. Now, what's nice, we talked about this in one of our other sections. I can't remember one of the Unit P sections. What's nice about polynomials? Polynomials are continuous over their domain. So I know that x plus 2 is continuous for all the points over this part of the graph, or over this interval of x values. I know that this is continuous from -2 to 2. I know that this is continuous for all x's that are greater than 2. What I don't know is what happens when we transition from one to the next. What I don't know is what happens at x equals -2. What happens when I go from this graph to this graph? Let me try that again. This equation to this equation. What happens at 2? What happens when I go from this to this? So I know that all of these are continuous. What I don't know is what happens when they transition from one to the next. So let's look at what happens there. So what happens? Let's look at it. Let's say it like this: continuity at x equals -2. Let's look at the continuity when x is -2. So what are the three things of continuity? There are three pieces to it. Number one, there has to be a point. So let's show that there's a point called f of -2. Okay, -2. I would not use this one because that's for all the x's that are less than -2. I would use this one because this is -2 less than or equal to. So I'm going to plug -2 into this. So that would be -2 squared over 2. That's 4 over 2, which is 2. So what have we just shown? We've just shown that there's a point, that the bridge exists. Now we need to show that the roads are at the same heights. So that's the one-sided limits. So the limit of f of x as x approaches -2 from the left equals. So all of these x values are less than -2. So if I'm coming to -2 from the left side, I would use this equation. So I'm going to direct substitute into that equation. -2 plus 2, -2 plus 2 is 0. Now, so I know the bridge from the left side of -2 is at a height of 0. Let's see what the bridge, or the road is, I should say, not the bridge, the road. Let's see what the road is on the other side. So now I'm approaching -2 from the positive side, from the right side. So that means I would plug in, well, we already did this, right? We already plugged in -2 into that, and we got 2. Uh-oh. Uh-oh. What does this mean? If the one-sided limit from the left is 0 and the one-sided limit from the right is 2, then I can say, so therefore the overall limit of f of x as x approaches -2 equals dne. Does not exist. So we are not continuous. Right now we are not continuous at x equals -2. Remember, the limit and the point have to be the same height. And we don't have a limit that exists. There must be a jump there. All right, let's look at the other side. So now I want to see what's happening at 2. Let's discuss the continuity at x equals +2. First of all, I have to show that there's a point. So which piece would I plug this into? This one has the x is less than or equal to 2, so I would plug it into this. F of 2 equals 2 squared over 2. That's 4 over 2, which is 2. Number 2, I need to now show that the roads are at the same height. So I want to figure out the limit of f of x as x approaches 2 from the left, and then the limit of f of x as x approaches 2 from the right. So this is, all these x's are on the left side of 2, so I would use this equation. We already did that, so we know that that's 2. From the right, that is also 2, so life is good. So if these are the same, then what I can do is I can take these together and say that the limit of f of x as x approaches 2 equals 2. All right, life is good at 2. Now we can just make sure that we want to do this kind of last statement. So therefore, f is continuous at x equals 2. Why? Because f of 2 equals the limit of f of x as x approaches 2. Okay, so that's good news. So we have continuous piece, continuous piece, continuous piece. This transition between x squared over 2 and 2 meet up perfectly, but this transition does not. So what we would do now is we would what's called discuss the continuity. So we would actually write up a little statement. Discuss the continuity. So what would we say? What do we know? We know that our function is continuous everywhere except for, over here we proved, I'm going to do a little write-up. F is not continuous at x equals -2 because the limit does not exist. So we could now say f is continuous for all x. That upside down a means for all x. That upside down a means for all x that are an element of, so I want to include everything except for -2. It's the only place we're not continuous. So I would go from -infinity to -2. Don't use it. Union with -2 to infinity. I would box it in and put it up on my fridge, and I'd be all proud of myself. So what's nice about this is we can use the idea of continuity to try to make sure that the two branches, the two roads coming in to the bridge are at the same height. So we can use that idea to help us create functions that we know are going to be continuous. So if I'm looking at this, if I want f to be continuous at x equals -1, what things have to be true? I have to show that the limit from the left, as x approaches -1 from the left, has to be equal to the limit of f of x as x approaches -1 from the right. So I have to show that the one-sided limits are at the same height. And for this to be continuous, the limits don't have to just be equal, but those limits also have to be equal to the function value, f of -1. Now, out of any of these, do we know any of these values? I don't know this yet because I can't plug in because I don't know what a and b are. I don't know this yet. I can't plug in and get an answer. I mean, I could get an equation, and we're going to do that in a minute. What is f of -1? I can get that because the function is equal to 4 when x equals -1. So I'm going to add that onto the end of my equation here. I know that this thing is supposed to all be equal to 4. If I want this f to be continuous at -1, then all these values have to equal 4 as we approach -1. So let's make that happen. Let's figure out what those values would have to be for a and b to make sure that these two hit each other. All right. Let's go with a nice, I don't think I've done any gray yet. I don't usually like to do gray, but let's try it. So what would be the limit of f of x as x approaches -1 from the left? That would be equal to, so which one of my functions is approaching -1 from the left? That would be this one. And what do we know about our x value if x is approaching -1? I know that that is going to be -1. So I would have a times the quantity -1 squared minus b. So my limit then as I approach the limit of f of x as I approach -1 from the right side would be equal to, okay, which one of these pieces approaches from the right? That would be this side. These are all the x's that are greater than -1. So I would sub in, direct substitute -1 for my x's. And what did we show that these things, for these to be at the same height, they had to be the same as the function value. So what could we set these both equal to? I could say this has to be 4 and this has to be 4. So now from here, I've got a system of equations. These two can come together to give me a system of equations. Let's clean this up. What's -1 squared? 1. So I would get a minus b equals 4. I clean this up. What's 2 times -1 would be -2a plus b equals 4. Now I can solve this like we did back in Unit 4 last year. Unit 4, I think it was. So a subtract 2a is negative a, minus b plus b is 0. 4 plus 4 is 8. So if negative a equals 8, then a has to equal negative 8. And if a equals negative 8, I'm going to plug that back in. Let's plug it back into this one. So if, I'll do my work on the margin over here. So a minus b equals 4. We just figured out that a was negative 8. Add 8. Negative b equals 12. So then b must be equal to negative 12. I like those. Those are kind of fun. All right. Let's see. From here on out, what are we doing next? So pretty much from here on out, we are looking at a couple practice problems and some other weird discontinuities. So let's keep plugging along here. All right. So if a function is continuous at the point, then the function value and the limit are at that same point. Let's just review that again. If a function is continuous at a point, what does it take to be continuous at a point? Then the function value, and when I say function value, I mean y value. We're in a fancy math class now. We call function values y values and y values function values. The y value, the function values and the limit values are, and they say at the same point, I kind of think of it as the same height. They're at the same y value. They're at the same place. When I say function value, that's what the graph actually is. Actual value. When I say limit value, that's the intended value. It's where the graph intended to go. Now, most of the time, limits aren't too bad to handle. I mean, if you can, you should always just try to plug and chug. Don't assume that there's a problem. If I want to figure out what the limit as x approaches 1 of this is a polynomial. I'm not going to have any issues there, so I can just start plugging and a chugging. So this would be equal to, if I put 1 in for all the x's, I'm going to have 4 minus 7 plus 3 minus 1 plus 1 minus 5. That would be what? Negative 3 plus 3. Negative 1 plus 1 is 0. Minus 5. Negative 3 is 0. I would get negative 5. So if you can direct substitute, this is what we call direct substitute. Try to direct substitute. Just plug and chug. So if I look at the next one, ooh, a little trigonometry here. So cosine of 5 pi over 3. Pause it. You should do this on your own. Let's see how you did. Cosine of 5 pi over 3. I'm counting by 60s. 1, 2, 3, 4, 5. Take that and blow it up. This is a 60. There's a right angle. 60 is square root 3 over 2. It's negative. Cosine is 1/2. It's positive. I want cosine. Cosine is x, so I would get 1/2. If you don't know how to do that, you're going to have to go back to pre-calc and look at some of your notes from that year. I've got some videos that you can go watch too if you really are struggling with your trig. But you've got to know how to do your trig. They just expect you to know trig. All right, direct substitute. That would be the natural log of e over 2. What does natural log and e do to each other? They cancel and they leave you with the exponent. So if you just have a plain old e, that's an e to the first. And so we're left with 1/2 here as well. So these, I can tell right away that these are all continuous functions because when I plugged in these x values, I got direct substitute gave me a value. The only time you're going to get a discontinuous function is when you plug in and you get like 0 over 0 or 5 over 0 or something weird like that. So we've talked about the two removable kinds of discontinuity. Removable. there are two kinds of removable discontinuities. The first one is a hole. I call this a hole. The other type of discontinuity I call a holy jump. And the difference between a hole and a holy jump is the hole has a point. So don't get a jump and a holy jump confused with each other. Now, don't use holy jump when you talk about if you're taking the AP test. Nobody else knows what that is. That's just something we use in this class. Then there are other type of discontinuities are called non-removable. These are called removable because they're easy to fix. Just fill in that circle. You would have to change one point. You'd fill in that dot. You'd now have a continuous function. You could take this point. You could slide it up until it's into that open circle. You have a continuous function. Non-removables are a pain because it would take a lot of work. It would take infinitely many, moving infinitely many points to make them continuous. Here's an example of a non-removable discontinuity. We call this a jump. Notice the difference between a jump and a holy jump. I kind of think of a holy jump as being in between a hole and a jump. Like you come into a hole, you jump out, but you jump right back in and come out the other side. Where a jump, you go into one side, you jump and come out the other side. Your bridge is at your two roads coming in are at two totally different heights. And then the one we're just about to talk about here, this is a big problem. This is what we call a VA, vertical asymptote. So let's formalize that. We saw another type of discontinuity in example 6. This was a vertical asymptote, a VA. They call this a non-removable infinite discontinuity, which, like I said before, I don't remember ever seeing that again in this class. So we just call them VAs from here on out. Similar to a jump discontinuity, the limit will always fail to exist, but the one-sided, we'll just skip all that part. Let's go. So the limit from the left equals infinity, and the limit from the right equals negative infinity, or the limit from the left equals infinity with the limit from the right equals negative infinity. We have what's called a non-removable infinite discontinuity called a VA. So let me kind of talk about this. Let's say I had the limit of f of x as x approaches 3 from the left, and the limit of f of x as x approaches 3 from the right. And let's say both of these limits were going off towards infinity. Then I would say that the limit of f of x as x approaches 3 equals infinity. This is a change from what I'm used to. I'm used to saying that anything going off to infinity does not have a limit. But if both of the limits are headed to the same place, we would say that that limit exists, and that limit is infinite. The limit of f of x as x approaches 3 from the left, the limit of f of x as x approaches 3 from the right. If they both are headed towards negative infinity, then I would have an overall limit of negative infinity as x approaches 3 from both sides. So what happens if one goes towards infinity and one goes towards negative infinity? That's what I think they were trying to talk about here. So I would say the limit of f of x as x approaches 3 from the left equals positive infinity. The limit of f of x as x approaches 3 from the right equals negative infinity. Then the overall limit as x approaches 3 would be DNE. Now, I'm not going to do the other case. Maybe I'll put it in parentheses, I guess. If this one's going towards negative infinity and this one's going towards positive infinity, then your overall limit would be DNE. I'm still struggling with this a little bit. I'm not sure if I buy that. I struggle with a limit that isn't infinite. That's not one-sided. But the two sources I've looked up says that that's fair game. So we'll go with it for now. And then if I change my mind or if I find some different information, I'll let you know. Okay, I think I'm going to pause here and do another video for the last bit.